as well. Now I would like to step back a little bit and look at heat flow or heat transfer from a macroscopic perspective. Heat transfer occurs in three different forms. These are conduction, convection, and radiation. We will be looking at each one of these cases and trying to understand the underlying physical principles. All right, let's start with conduction. When we discuss the flow of heat in a confined box full of gas molecules, we made an assumption. The assumption was we kind of glossed over how heat actually penetrated through the walls of the box. We also didn't pay attention to how heat traveled from the heater to the box. Okay, we just kind of assumed that miraculously that heat just traveled from the heater to the box and just zipped through the walls of the box, and it was absorbed by the molecules of the gas. So we have to be a little bit more careful and explain how all that happened. But fortunately, with what we have learned so far, to explain that is really not that difficult. So let me use my red pen and put a heater here. So again, I have a box full of gas molecules, and I have a heater, and this heat is coming from my heater. It's radiated out. Okay. So first, I think we have to explain how that heat travels from the heater all the way to the box. Okay. Well, that's easy because that gap is filled with air molecules. And air molecules, just like the molecules in our box, they are in random motion. And their energy is going to be determined by temperature, and each molecule will have an energy equal to K times Boltzmann constant times temperature. The point is, the heat that comes off the heater will be hitting the molecules that are closest to the heater first. So I'm referring to these molecules right here. And their kinetic energy will increase. When that kinetic energy increases, well, they will be colliding with these neighboring air molecules, and just like the molecules inside the box, they will be transporting that energy through collisions slowly but surely from right to left. So I think we can agree that this energy will be slowly moving toward the box. Okay? And eventually, those hot air molecules will be colliding with the atoms of the box. Now, in this case, not molecules, but atoms of the box. So now we have a solid. The situation is very different. The solid atoms are not able to move around like the gas molecules. They're kind of tied to their places because they have bonds, chemical bonds, that are tying them to their places with respect to their neighboring atoms. Yeah, they cannot leave their places. They cannot travel around, but that doesn't mean they cannot move at all. In fact, they can vibrate. So, through those vibrations, these atoms, just like the gas molecules, can transport the energy to the gas molecules inside the bunks. So just like the molecules wandering around, when these atoms begin to shake more vigorously, well, the probability goes up. They will have more collisions, and that energy will be transported. So that's how actually the energy from the heater goes through the solid wall of the box. And you know the rest. The rest is basically the walls begin to go through collisions between the gas molecules inside, and that energy is transferred. And slowly but surely, the heat flows from the right to the left. Now, assuming that we do not have a temperature differential between the two ends of this experimental setup. That is, we provide the heat for a while and then stop and so forth. This temperature differential cannot be maintained. So the point is, this process of transporting heat from right to left is going to continue only if we have a temperature differential between the two sides. Okay, if we don't have a temperature differential, then there is no incentive for any energy transport. So this is a key principle of this conduction mechanism. The idea is that our universe likes to be fair, and equilibrium is really the rule of the game. And in this case, we are referring to temperature equilibrium. What makes this process happen is the fact that we have molecules, gas molecules, on the cold side, which are not energetic at all. Their kinetic energy is much less. And on this side, we have molecules with very high kinetic energies. So that difference makes the heat flow from right to left, because simply through those collisions, that excess energy on the right is being transferred to the molecules on the left. So slowly that energy is moving. But if we continue this experiment and the cold side starts getting hotter and its temperature goes up until this temperature differential disappears, well, there is no mechanism for conduction to transport the heat. So everything stops. So, rule, we need to have a temperature differential. So this will become more hopefully clear when we write down the equations for conduction as well. But before that, I would like to look at what happens in a solid more closely. So as we discussed, in a solid, the atoms cannot leave their places and travel like the gas molecules. They're kind of attached to their neighboring atoms through chemical bonds. But interestingly enough, the energy of the atoms can be transported through these chemical bonds. And it is easy to look at these chemical bonds as springs. What we are talking about is that if you have one of these atoms kind of shaking because it is energetic, well, it is not independent of the neighboring atoms, because we have these chemical bonds actually attaching them to the neighboring atoms. So in this case, these atoms are not shaking like crazy to collide with the neighboring atoms. But nevertheless, the neighboring atoms can feel the movement of these atoms. And so through the bonds, through these springs, the energy of the shaking atom can be transferred to the neighboring atoms. So this way, the energy can slowly go from one atom to another. Again, in this case, we do not have any collisions, but yet still there is a type of physical interaction between the entities. So because these atoms are vibrating, they result in some lattice waves. And these lattice waves, as we have seen before, are called phonons. Okay? So in this case, the heat is carried by phonons or waves of the lattice. Phonons are actually very similar to photons in a way. If you recall, the energy of a photon was given by Planck's constant times the frequency of the photon. Well, if these atoms are resulting in some lattice waves, we can talk about the frequency of lattice waves as well. And in fact, the energy of a phonon is exactly equal to Planck's constant times the frequency of the lattice wave. So same equation we have for photons also applies to phonons. So therefore, phonons can function just like molecules in a gas to transport heat in solids. But that is not the only mechanism. We have another very important heat carrier, and that is electrons. So in solids, we have therefore phonons and electrons as two possible heat carriers. And in some solids, phonons are more dominant, and in some solids, electrons will be more dominant. Now, there's a big difference between phonons and electrons. And in fact, electrons are much closer to the gas molecules because electrons can leave their atoms and they can freely wander around just like gas molecules. So they can go through collisions just like gas molecules, and in those collisions, they can transport energy from one electron to the other. So then, in which materials phonons provide the dominant heat conduction mechanism, and in which materials electrons are more dominant? Well, the answer is, if there are materials with very few electrons, then I think it's reasonable to assume that those materials will have the phonons as the dominant heat transfer heat carrier. Well, what are those materials? Well, insulators. Insulators will have very few free electrons. And for conductors, electrons must be the most dominant heat carrier. Now, this makes sense, but what about semiconductors? Something like silicon. That's interesting. In that case, the jury is out because it really depends on how many free electrons or the concentration of free electrons in the system. You can make a semiconductor metal-like by providing lots of free electrons. So how do we do that? Well, we learned that we have a process called doping, which adds lots of extra electrons. All right, so let's look at that more closely. When we discussed semiconductors, we talked about two types of semiconductors. The first type was intrinsic semiconductor. Well, in the case of an intrinsic semiconductor, the material does not have any impurities. So if we are using silicon, it's silicon as pure as it can be, and this material has a band gap. And band gap is defined as the energy gap between the valence band and the conduction band. So EV and EC, as you recall, are referring to the top of the valence band and the bottom of the conduction band. And again, at 0 Kelvin, the valence band is completely filled and the conduction band is completely empty. But if we raise the temperature of the semiconductor to room temperature, then the carriers, the electrons in the valence band, find enough energy to jump from the valence band into the conduction band. And when that transition is made, we have a free hole in the valence band and a free electron in the conduction band. So now when this transition happens, this electron is a free electron. That means just like the molecule in a gas, that electron can choose to leave that location and go as it pleases itself. So those electrons, as they are free electrons, they can go through collision events just like gas molecules, and they can transport energy through those collisions. Now the question is, do we have sufficient number of electrons through this mechanism to say that, well, this is a really important heat transfer mechanism in a semiconductor? The answer is no. Through this process, you're not going to have a very large concentration of electrons in the material. For instance, just to give you some numbers, the intrinsic carrier concentration is 1.45 times 10 to the 10 per cubic centimeter in silicon. So intrinsic carrier concentration is the electron concentration or the hole concentration in the materials. For every hole, there is an electron. So that's 10 to the 10. That looks like a large number, but actually that's not a very large number. Now, the other type of semiconductor that we talked about is the extrinsic semiconductor. So in the extrinsic semiconductor, we again have the band gap of the material, but we have some energy levels for the case of N-type materials close to the conduction band with electrons which can easily jump with very little energy to the conduction band, providing free electrons. So this is the N-type material, N-type extrinsic material. So this way, I can add impurities that result in these defect states, which we refer to as donor levels, that provide a very small gap between the conduction band and the donor levels, such that these electrons are easily excitable to the conduction band. And this way, for every impurity atom that I add to the material, I can get an electron. And just to give you an idea, in silicon, for instance, the electron concentration using this method can be 10 orders of magnitude higher than the intrinsic carrier concentration. So we can go up to electron concentrations as high as 10 to the 20 per cubic centimeter. So this is huge. Now this is a game changer. Now in this case, the electron concentration is not sufficient to say that this can be a dominant heat transfer mechanism, but in this case, this is different. So the moral of the story is that if you have a very heavily doped semiconductor with lots and lots of electrons, then yes, you can have electrons carrying a lot of heat. But for intrinsic semiconductors, you don't have sufficient number of electrons. Phonons will be the dominant heat transfer mechanism. So this basically concludes our discussion on how heat travels from a nanoscale perspective in solids. To repeat, we have phonons, lattice waves, in insulators and lightly doped or undoped semiconductors, and we have electrons in all conductors and heavily doped semiconductors. The point is, whether you have phonons or electrons providing you the heat transfer mechanism, your heat carriers are physically interacting with each other.